Hello and welcome back to our Coding the INI Parser in our C++ tutorial series here on the Ludwig Fusel channel. So in the last video we have properly factored out all of our INI Parser code into a separate C source file and into a C header. Now what we want to do today is we want to continue on and improve our library and also introducing new features that you don't know yet. So today what we want to do here is we want to remove that code here. I don't want to have the INI in the application itself, in the main, the source file, because the source file gets compiled and really it's not the point, like having all the control characters and stuff like that. It's not looking good, it's looking ugly, it's not the point of it, because it's an INI configuration file, which has meant that the user should actually be able to change it at not runtime, but like between starts of the application to actually customize how the application works. And this doesn't work if it is hard compiled into our source. Really, it's just the point of wasting memory, wasting computational power to parse this. So what I want to do today is I want to remove that from here into a dedicated file. So what I basically want to do is I want to add a file to my system that I can later on also distribute, because I also of course have a video on distribution of your application. And yeah, basically what we want to do here is today we want to create a file called config.ini, and this config.ini shall contain all these configuration data and then is responsible for configuring the application. So the first thing that we want to do is we want to add a new file. I'm going to add this file to the project. You could add this to any location where you desire to do. Could add this to any location. The only thing that you need to be concerned about is that this file is reachable at runtime, but we're going to talk about that when we get to it. So what I want to do here is I want to right click it, say add new item. Then I'm going to go to, it's already selected here in my configuration here. You want to go to util text file and you want to name that file config.ini and then press enter to add the file. Now you can also see that Visual Studio has detected it in here, it's in there, it has detected it as a actual file. You can see the cogwheel here down there, which indicates it's a configuration file, and we are ready to paste in our INI code. I'm going to quickly open this up. So here we have our INI template. Let's actually steal this again from Wikipedia, paste that in, assert my formatting, add some source information, so source, where we got that one from. It's from, let's go to the main because I already have it in here. Steal that link here, paste it in there, and we are good. Well, here you can see, ready to go, our new INI configuration file. Now in the main, I actually want to completely remove this here because it's no longer required. We just want to parse our INI file. However, this is not going to work because we no longer have the INI file as a variable. So now you'll be tempted to just say, alright, config.ini. But surely enough, if I call this config.ini, it will not work. It's gonna output us nothing. Why is it outputting us nothing? Because this is a file name, and a file name is not gonna work as an INI content string, because as you remember, our function here, parse.ini, requires the actual data of the INI. So what you need to do is basically replace this config.ini with the data of the file in a dynamic way. So actually reading the data from the file. And that's what we want to do in the video today, working with files. Now, before we work with files, there is one very important information about file and file paths. Now, to get the path of that file, you can actually see that we have a full path down here in Visual Studio. So you would be tempted to just take that full path from here and paste it in here and say, all right, the full path is that one. I mean, yeah, it's actually now having issues with the backslashes. So after adding the double backslash here, you would think that this path to the file might be good. However, this path is totally wrong. I mean, yeah, it will work. This path, later on when we are using the proper functions, I mean, currently it's not supporting files, but later on if it supports files, this path is going to work. It's no problem. If you start this on your system with the path you have copied, it's gonna work. But it's going to break down as soon as you're distributing your application to a other computer, because then the configuration files might be stored wherever the user installed the application. So the configuration file could be anywhere. I don't know if the device where it was installed is C, if the subfolder is called programs, if the subfolder is called programs INI parser. Really, you have no idea where that file is stored. No idea. Totally no idea. And that's a big important information. You will have no clue where that is stored. So how to solve that? You can use something called relative file path. If you're doing that, you're basically telling the runtime, the Windows, the Linux, the whatever operating system your application is running on, you are telling it to look in the current directory. So / means current directory, while that one is an absolute path. That one is an absolute path that only works on your system, or potentially only works on your system. You might be lucky and it works on one other guy's computer as well, but you're gonna have like 100 users, maybe one of them has the same folder structure. Okay, if you're installing in like the default applications, it might be quite certain that it works, because by default Windows calls the default disk C, and it's always program files, and if you're always having that installed in C at the exact same directory, it works. However, this is not how you do things. What we want to do is we want to handle this with so-called relative path. A relative path is relative to the current location. Now, the current location does not need to be mistaken by the location of the exe file. If you're doubly clicking an exe file, the current location, the executing directory, the so-called working directory, is the location, the folder where the exe is located. However, this might not always be the case, just to be aware. Later on, you're going to see that our exe is in a total different place in our INI configuration file. However, that path, that relative path, current directory config.ini, will work inside Visual Studio. But as soon as you're trying to start the exe outside of Visual Studio, it's going to fail and not going to find the file. This is because the working directory, the current directory, the relative directory to which we are relative, in this case, depends on the configuration of Visual Studio. If we start debugging in Visual Studio, it's going to explicitly set the working directory to a certain path. Actually, you can do that. For example, if you're writing a Python script that uses subprocess and starts your application wherever you like it, or starts your application the way you like it, you can actually tell that Python subprocess function where to actually set the execution directory, the working directory. You can also, of course, do this with C APIs. If you're using the native Windows APIs or the native POSIX Linux APIs, you can tell it where the working directory is of a process that you want to start, an application that you want to start. But that's very important. The / always means working directory. Well, how can we find out what Visual Studio uses as a working directory? We can right-click our project, go to Properties, go to the Debugging tab, and take a look at the working directory. Now you can currently see that on all configurations and all platforms, our working directory is the project directory. And if I would take a look at the project directory, you can see that in this case it's C, users, tutorial, documents, CCP tutorial, 04 INI parser, which happens to be the folder where all of our source is stored in here. So if we have that config INI next to our source files, it's gonna work, because this is how Visual Studio defaults to that. By default, Visual Studio starts at the source directory, the project directory. And this is why we have put this in here, because to make things simple, we just need to put it next to our sources. And as soon as it's in Visual Studio, it's going to work by writing /, which is a relative path, to our working directory, in this case, in the default Visual Studio environment, to our project directory, which is the directory here. And we can then say, all right, I want to get the config.ini and read from that file. Now, file topic back to the side. Don't care about these now, about path. We just now know that this path refers to our config.ini file, and what we want to do now is actually read it. So what do we want to do? First of all, this parse ini function is not going to be sufficient handling that. Of course, we could change this function to not take the raw ini data at all, to just take always file paths. However, this is not what you want to do. In a real-world library, you want to have the flexibility so that the user can actually supply raw data, because the user might have its own implementation of opening files. Because, for example, especially on a game engine or on anything else, Maybe on an application that has advanced configurations, you might want to first check in the working directory. If the file in the working directory exists, take that one from the working directory. If it does not exist, you might want to search the user documents folder or the configuration folder of the user, check if there is a configuration file. If not, change the default one at the installation path. And if this even fails, you might want to read one that was stored inside the exe like we did it previously. So there might be some logic attached to it. However, we're not going to do it, but we don't want to, of course, take away that flexibility to do it. So we want to keep that function, and we want to add another function that is responsible for reading it from files. Now, of course, we're not going to copy paste the content of our parse ini function. Of course, what we're going to do is we're going to read all of our file content into a string, into a char buffer, into a char array. And what we're then going to do, as soon as the char array is finished, we're going to invoke the function parse ini. So basically, we're going to add a function that calls our function that we have already written, which also means that we don't need to change that function here at all. So let's start by writing in your function here. So parse, it's going to call parse again as well, parse ini, but now I'm going to append a from file. Const char pointer file path, so path to a file. So now it's just a matter of calling that function, and everything will be fine later on when it's of course implemented. Now what you could do now is you could copy that signature and do it all manually and create the new manual head of that function and body. However, as soon as we are in that architecture of H and C files, Visual Studio has a nice little handy tool. You can see that this is underlined green. It says function definition for ini parse ini from file not found. But what we can do is we can left click on that wrench here, and we can say create definition of ini parser and file in ini parser.c. And if I click that option, you can see that we are getting a little peek window that shows us our C file, and you can see that the head of that function has been auto-generated. Now clicking on that button here will promote this to a full open editor, and you can start coding. Now it's just a matter of reading that actual file. Now, how do you open up files? Well, first of all, a file has the data type file. File stands for a file. And in our case, the file is a pointer, because it's going to be allocated by Microsoft. So we're going to have a pointer to a file which we want to open. So if we call opening a file, if we call it function, you're going to see in a second, Microsoft is unallocating this file data for us, and we get a pointer to it. Now I'm just going to call it file here and set it initially to null. Now to actually open the file, you are calling a function called fopen. All file functions are prefixed with an f to basically open it. And you can see that we have a function called fopen that returns a file pointer, takes a file name and a mode. Now, this function is actually unsafe, and I'm going to spare you that finding that out that it is actually deprecated. So what we want to use is the safe version. So we want to use the file, so the fopen _s. Now fopen _s works actually from a functionality the same than the normal fopen function, but it has a bit of a different syntax. Now the first parameter is going to be the hardest one to understand, because I think we haven't talked about pointers to pointers, double pointers. I think we haven't talked about them. The first parameter is a file pointer pointer. So we already know what a pointer is, right? A pointer is a address. So a pointer is a address to a certain type. In this case, it was a file pointer that we are trying to get. So we get a pointer to a file. We have the address where that file is actually stored, or that metadata for that file. However, that is done. We really don't care what's inside this file data type. That file data type. We don't really care about this. It's managed by the operating system. We don't care. But what we do is we obtain an address, a pointer to it, so that we can work with it. Now, what does this function need? It needs a pointer to a pointer. So basically what it needs is the address of your variable. So it needs the address where you are storing the pointer to that file. So it takes a pointer to a pointer. This is why we have the double pointer. You give it the address where you have stored your pointer, so that this function can then dereference the pointer and actually modify that value and write the correct pointer to that. If you haven't got that, maybe skip a few seconds back and listen to that again. A pointer to a pointer isn't that complicated. It is the address of your variable, which happens to be a pointer. So it's a double pointer. That's the only magic behind that. So what we give it is where we are storing the pointer, so that the C library can then assign a pointer value to our variable, to our pointer. And this is the only reason why it's a double pointer, a pointer to a pointer. In the Microsoft syntax and graphics programming, often referred to PP. PP, pointer, pointer. But yeah, so what we basically need is we need to tell it where we store our pointer. How are we going to do this? Well, we're going to give it the address of our pointer, like that. Now we need a file name. With the file name, they really mean the path to the file, so very straightforward, just pass on the file path. Now the actual mode is now going to get a bit more trickier, and to give you a few informations about the mode, we're going to take a look at this function on the C documentation, and I'm going to open up fopen here at the CPP reference and show you what this means. The mode here is a null terminated character string determining the file access mode. Now, what is the file access mode? The file access mode is a combination out of two values, or not two values, it actually are three ones where two are optional. So the one that is always required is the mode: read, write, or append. How does it work? If you want to read from a file, you're just going to get permission to read the file. If you're trying to write it, it's going to fail. Also, if you're reading the file, you want to read it from the start. If you want to write to a file, you get permissions to write to that file, creating a file for writing. The file already exists, it destroys it. If the file doesn't exist, it creates one. While on read, if it doesn't exist, it fails to open it, and if it exists, it reads from the start. So reading, writing, quite simple. Now we also have append. What is append doing? Well, append is basically a special form of write. It appends to a file. If it doesn't exist, it creates a new one. And if it already exists, alright, it starts writing at the end of the file. It does not clear its content, it just writes through the end. Especially useful if you are writing logs, right? If you're writing logs, you want to periodically write to that file, so you want to always append to that. Now you can also optionally put in a so-called plus. How does that plus work? That plus basically says, okay, extended attributes. Read extended opens a file for reading and writing. It's going to read from the start, and if it does not exist, it's going to give us an error. However, you still have the option to write to it. Write extended creates a new file for reading and writing. So again, read and write. If it exists, it destroys the content. If it's not existing, it's creating a new one. You can write to it, but you can also take a look what you have already written to it. So you also have readabilities. Appending, same story. You can just by default start appending to the end, but you can of course also read from it. This is just some extended versions if it's not sufficient to just read, write, or append. In our case, it's really simple. We just need read. But do we really just need read? Well, you might think yes, and you're gonna write code and you're gonna have issues and you don't know where the issues are coming from, and you're gonna quit C because reading files doesn't work and you have done it exactly as the example did it. Well, actually, reading files like that is not done very often. I think I've never encountered I never encountered actually reading them normally. I always read them in a special way. I read them in a special way, which is described here. File access mode flag B. This is an optional flag that can be specified to open the file on binary mode. You can also see that this flag has no effect on POSIX system, but on Windows it disables special handling of new lines and whatever. So basically this binary one is just relevant on Windows. If you do it on Linux, it's just ignoring it, so I'm gonna tell you, just take it with it. Bad things are going to happen if you don't use it. You need to use it, at least in our case. So by default, normal file on Windows has special handling of new lines. We don't care about special handling of new lines. We're going to parse that raw file ourselves. So we're going to add this optional B. So we're going to say RB for read binary. Now, after calling that function, we should have a file that's available for reading. So what we basically just going to do is we want to check if our file exists. So if the file pointer is valid, we have an open file for reading. Now, of course, this file needs to be closed at some point, because same with malloc, we allocate something, we retrieve something. When we are done with the file, we have allocated that resource, even through this might not have allocated memory. It probably has allocated memory in the back, but we don't care what it's doing in the back. But if we are done with that file, we want to close it. Especially if we are opening this file for reading, it might get locked by the operating system because we are reading from it, so nobody else can write to it or read from it. So we want to make sure to call fclose when we are done with the file. Open, close, fopen, fclose. Closing the file. And now let's actually put a breakpoint in here and see if we reach it. Press F5 and see what we get. And surely enough, we are getting a breakpoint here before that fclose, which means that our read binary open of that file was successful. So I can continue on and of course get no output, but know that my file has been opened successfully. Now you would think that you now want to read from that file. So let's actually take a look how you can read from a file. So the function is called fread to read from a file. Now, how can you read from that file? Let's take a look on how that function looks like. fread, if we take a look at it, takes a buffer, size, count, and a stream. So how does that work? Well, first of all, the buffer is the output buffer to which it tries to write data. So your target, your array where you want to store that string. It takes a size, how many bytes you want to read, and it takes a count, how many of these sizes do you want to read. Now you might think, why is there not just a total one? Well, basically the idea is internally it's a loop. It's going to read size, amount of bytes, gonna check if it can read size again, then it's gonna read size again, and as soon as it fails, it kind of like says, all right, I'm not able to read size of whatever, so I'm gonna return. So basically, if you're trying to read single characters, then you would have a size of 1 and a count of a certain number, and then the function is gonna return you something. The return value is gonna be how many elements of size were able to be read. So if you have a size of 5 and a count of 3, but it can only read 10 bytes, it's going to return you 2, because 2 or 10 bytes that has been written is 2 times size. In our case, we just want to read the whole file as one thing. So we're going to have the size equal to the file size and the count to 1. Last parameter is the actual file where we want to read from. So we need a buffer to read to, so we're going to have a char pointer. Let's call it file content equals to null, and just leave it as null just to get started here. File content, then we need a size. It's of type size t, file size equals 0, and size t, I don't know, I think I already told this to you, but I don't know if I have cut it out, so I'm going to tell it to you again. Size t basically means an unsigned integer as big as the architecture. Architecture means the architecture of the application. So if your application is built for 32-bit systems, this is going to be a U in 32T. If you're on a 64-bit machine, it's a U in 64T. It's just how the library rolls. So I'm just going to assume a file size of 0 here for beginners, and a count of 1. Now finally just add the file parameter here and we are good. Now to validate that this function worked correctly, I told you it's going to return how many counts were possible, since our count is at a maximum of 1, and if it fails a 0, we want to validate if it's equal to 1, and as soon as it's equal to 1, we are actually good and we can continue. So basically this here now said read success. So we successfully read our file. Now you can see that we have two problems with that code, how it's in here currently. You can see that our file content is a null pointer. So null pointer means that we can't write to it. How would we allocate this? Well, we would allocate this the size of the file. So file size, which obviously needs us to put that line below of the file size. So allocating the buffer, very simple. We call malloc with the file size, and if that succeeds, we continue on. So if file content is a valid buffer, we're going to do stuff, and of course, if we no longer need it, we're going to free our file content buffer where we stored our data. Now you can still see that this code still has one issue. File size is 0. Now, how can we get the size of a file? Now you would expect that we have a function called fsize, right? But no, there is no function fsize. I mean, yeah, it's kind of like showing that there is one, but you can see it's not yellow. There is no way in C to know how big a file is. Or there's a way, but there's no native function in C that tells you how big a file is. So you need to kind of like do a trick with that. And the trick is to understand how files work. How does that file pointer work? Well, basically this file pointer is a so-called handle. Or the library itself calls it a stream, so handle is not correct, but the Microsoft term is handle. And since we are on the Windows platform, this internally maps to a Microsoft handle to a file, which uses the Windows API, which you could use in C as well directly. But that's not the point. So basically, this file pointer is a handle, and this handle is some metadata around a file. This metadata knows where the file is stored. This might directly know on Windows what the address of the PCIe device is, where it's connected to, or the Windows virtual hard drive ID, whatever Microsoft does in the background. Basically, this handle has all data that Microsoft needs to read that file. It might also contain a buffer where it pre-cached contents of that file. It might contain a buffer that is therefore writing to that file, which sequentially gets flushed to that file, but not on every write, maybe just on close. Like, really, there could be anything. Behind that file pointer could be anything. And the C language does not like apply a restriction on how this works. The C library just tells, all right, these are the functions, this is how they should operate, but how you're going to implement that, Microsoft, we don't care. Implement it how it works for you. So we kind of like need to come up with a different concept. Really, we can't just use that file pointer and just index into that like an array. Basically, what this file pointer does, and this is associated with the C library, is it contains a file position indicator. Cursor, however you want to call it. And this file position indicator indicates where you are currently in that file. So that is a pointer basically as well, indicator pointer, that points inside of the file, starting at 0 at the origin of the file and ending at size of the file -1, or yeah, size of the file -1, to actually indicate the end of your file, the last character in your file. Now, basically, you can abuse this file position indicator to get how big the file is. In general, the file position indicator, it's used for reading and writing. If the file indicator is at the start of the file and you're reading from the beginning of the file. This is also why read told you that it's reading from the beginning of the file, which basically means starting at the beginning of the file with the file position indicator. Appending, on the other hand, meant that the file position indicator is at the end of the file. So if you would write, you would write at the end of the file. So the file position indicator is responsible for controlling your read and write operations, or kind of like providing a start positions to them. And of course, if you are using this file position indicator for reading and writing, you need to have a way to manipulate that file position indicator. And you can actually do this by using two functions, a function called fseek and ftell. Now, fseek is therefore seeking a position in the file. So kind of like searching a position, moving to a position in the file, moving the file position indicator. So basically, fseek, move that position indicator. Now, what you can actually do with that fseek is you can tell it to seek to the end of the file. And you can tell it to seek back to the beginning of the file. And this comes in handy with the next function, ftell, which is responsible for telling you where the file position indicator is. So really, to get the size of the file, you basically say, hey, file position indicator, move to the end of the file. Hey, file position indicator, where is your location? Oh, I'm at that position. You know, it's at this position. This is how big my file is. And then, of course, hey, file position indicator, go back to the beginning so that I can read. So this is basically how things work. You can modify this file position indicator. How do you do it? I already told you that. fseek is the function that we want to use. First parameter is the file, very simple, our file handle. The next thing is the offset, and the next thing is the origin. So offset and origin. Really don't know these, so let's take a look at the documentation and see what these mean. Now, fseek. Okay, let's take a look at the offset. Number of characters to shift the position relative to the origin. Okay, so we have kind of like an origin, and we have a number that is actually can be negative and positive to kind of like shift from that origin into each direction, how you desire it. Now, this offset comes together with the origin. So let's take a look at what the origin means. Position to which offset is added. It can have one of the following values: seek set, seek car, and seek end. Now let's take a look at this. Seek set, seek car, and seek end. What is that? Okay, this is all referring to the same document. We need to scroll down a bit. And you can actually see here we have some description of that. So seek set means indicate seeking from beginning of the file. Seek car means indicate seeking from the current file position. And seek end means indicate seeking from end of file. So set means begin of the file, car means current position, and end means end. So really what we can do to get to the end of the file is apply an offset of 0 because we don't want to move it from the end. We just want to move it to the end. So this basically means, hey, go to the end and offset 0. So go to the actual end. If I would do something like -5, it would say, okay, go to the end and 5 characters back. So you would be able to read the last 5 characters of the file. But we just want to move it to the end, like that. Now I told you that we also have the function ftell. Ftell gives us the current position of the file. It just takes the file handle in here, the file pointer, and gives us the current position of the file position indicator. Now you can see it's a long that is returned. However, this is never going to be negative, so you can just assign this to your file size like that. So ftell just tells you where the current indicator is. And end actually means that it's already there at the last byte, so you can directly assign this. You don't need to do math with that. Now, if we would now directly read after this operation, we would fail. Why would we fail? Because we are now at the end. And if we are reading from the end, which would occur an end of file error. And an end of file error means actually that you are at the end of the file. So if fread fails, so is equal to 0, you could use the feof function. Of, which stands for end of file, and this is going to return your 0 or 1 depending on if end of file has been reached of your file. This is just a diagnostic function not really required here because we know how big the file is. So basically what we need to do, we need to add another fseek for the file, 0, and seek set, which is at the start of the file. And actually there's one more function here that can help us with that, because going back to the begin of the file is used quite often. So we actually have a function for that. Let's see if it's in here. I'm not quite sure if this is actually a... Yeah, it is actually a real position. You can actually see that we have this this rewind function here. This rewind function basically moves the file position indicator to the beginning of the given file stream. This function is equivalent to fseek stream 0 seek z. So we can just call the rewind function to do not too much typing. So rewind the file. So we're going to rewind it to the beginning, and now we are ready to read. Now read success should be good, and we should then now be able, after we have read the content, to call our ini parse ini function with the file content in here. Now let's actually make a breakpoint in here before we go into that, and remove the breakpoint here. Maybe let's also put a breakpoint in here before we allocate and before we read, so that we can step through this very, very easily. So now let's press F5 and see what this does. So first of all, let's take a look at the file size. You can now actually see that the file size is 315, which means that it seems to have worked. We can actually verify this, 315 bytes. Can we see that? Well, let's go to the directory. Let's click the ini config, and you can already see if I click it down here, 350 bytes. This might not be shown to you if the file is bigger. If you really want to see it, you can go to the properties and you're going to find how big it is here. So 350 bytes. I don't know why the size on disk is 0. Probably because this is like a VMware system, which is virtualized. Nobody should have something here as well. But you can basically always see the number of bytes here in the brackets. If your file gets bigger here, there's then maybe kilobytes, but the actual bytes are always going to be displayed, which you can one-to-one cross-reference with your debugger output. And in this case, it's exactly the same, which meant that our application was able to get the file size successfully. Now let's continue on. Yeah, malloc also succeeded. We have an invalid characters in string range, which is good. Or, yeah, okay currently. Now let's continue again. What the read does, read succeeded. And it looks like that our content is in here. We can click this view button to check if our content are actually good. And really, we are not getting what we expect. We are getting the address. We are getting beginning quotation marks. We are getting unformatted data with R and N. So reset a new line. And instead of getting the whole file, we are getting ... What does that mean? Well, this means that Visual Studio was not able to find the end of that string. So Visual Studio was not able to find the null terminator, and we could try to verify this. If I close that window here, copy that pointer, paste it into the memory view, and we would try to start and search the null terminator, you can see that we don't get one until here. But actually, as you can see, before we are getting then the first null terminator is actually already there. No, there is the first null terminator. But you can actually see that before we got that first null terminator, we already had some invalid data in here. And with invalid data, I mean this FD, 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 DD, 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 D. This is invalid string data. This is something that Microsoft can detect and see, right, this is not looking correct. And it can also reference this with its own memory management tables and see, all right, actually the string is bigger than the buffer that has been allocated for that. And this is what Visual Studio catches and then points us out with these 3 dots. Now this is dangerous, because if I would continue on here executing, it seems that it kind of worked. However, it did not. It did not work because it actually read more than it was supposed to read. I mean, very quickly ignore that this is looking a bit ugly. That's actually okay. We're going to get to this in a second. But just ignore what happened here. We have read too many bytes, but it worked. And these are sneaky bugs, because these bugs might not be an issue when you are debugging. You didn't get an issue. Microsoft did not alert you. The compiler did not alert you, the debugger did not alert you, the runtime checks didn't alert you, nobody alerted you, and the code actually worked. If we wouldn't have that bug, that we would have the other way anyways. And if these bugs are in there, it might be fine, right? As soon as you're switching to release and distributing your application, and it runs on a system where it matters and it crashes. Or not crashes, or might crash, give you invalid data, give you configuration values that are not even in there, appending some stuff. Maybe if there is anything else already stored in memory that was also happened to be a string, then you might modify the last setting that has been read from that file, and bad things can happen. And this is an issue. Now, where is the source of this issue? We have a missing null terminator. Why do we have a missing null terminator? Well, basically we have a missing null terminator because we have read the whole file. Now, what is an issue with writing the whole file? Well, the file is ending with that character. What is that character? This is a tab. So the file ends with a tab, not a null terminator. A file is not null terminated. A file is bound by its size, not by a null terminator. Why does the file has no null terminator? Well, because the binary file could have as many nulls in there as you desire. In a file, you can write 100 nulls and it doesn't care. It's a binary file. We don't care. It's not a string. So what we need to do is manually put a null terminator at the end of the file. Yeah, surely, I could now copy a null terminator from any online source or do some tricks to get a null terminator in Notepad++ and paste it in here. But that's not really the case, because the user is going to probably, at some point when it configures the file, sees, oh, what's that? That looks ugly, delete it. So what we need to do at our application is, we need to go one byte ahead than the file that we have actually read, and we need to manually insert this null terminator at the end of the data that we read. So basically what we want to do, instead of our 99 parser, we want to allocate 1 byte more than our file's actual big to have space for the null terminator. And after we successfully read the file, we want to go to our file content, actually to the end. What is the end? Well, it is file size +1, and since we are negative indexed, -1, which is basically just equal to file size, and we want to manually insert a null terminator at the end of that read data to make sure that we have a proper null termination in our string. Now if I hit F5 and debug this once again, and open up the file content once again, you can see that it directly looks better. We have the whole data in here, it's formatted, it looks good, it does not have ugly addresses or quotation marks, and we got exactly what we saw in our text file. And now we are good and rolling. If I now continue on, we would expect to have a fully functional working example. However, we do not. Why do we not get this? Actually, I have a clue, but I'm not quite sure if that really is the case, what is happening here. there's one big difference between the file how we have it here and how we had it previously in our source file. In our source file, we terminated the line with \n. However, on Windows, it's terminated with \n, \r, or \r/n. I don't know the order now, I've forgotten it. But basically what Windows inserts is, at a new line, Windows is inserting 2 control characters. And we have never actually cared about control characters. So what I want to do now is I want to rigify our code, especially our append buffer code. I'm going to start by our append buffer function to basically take control characters in mind. How are we going to do this? Well, I don't know. We're going to try it out and we're going to fix it until we are done. Let's go to actual ini-parser.c and scroll a bit down to our append buffer function. There it is. Currently, we are just, no matter what we got as a char, we are just going to commit this. So what I want to do is I want to put a special constraint in here. I'm just going to write an empty if, and only if that if is fulfilled, we're going to add this. Now, we have multiple ways of checking characters. Actually, let's open up the documentation and see if we find a function that is good for us. So let's go back to C here and go to string library, null terminated byte string management. And you can see that we have many functions here. Now, isNum checks for alphanumeric characters, lowercase, uppercase, we don't care. Digits, we don't care. Hexadecimal digits, we don't care. We can all add these. Graphical characters, spaces, blanks, prints, and ispunct. We really don't care about these. These are just special type of readable characters. We actually just care about this isCntrl, which is checking if a character is a control character. So what we basically want to do is we want to check if C is a control character, and this function might not be there, which is exactly the case because it's inside of the C types header. So we want to make sure, actually I'm an idiot, we already refactored that. We need to add it here. We just need to make sure that we include the C type header here as well. And now this one should be detected. Yeah, now it's detected. And only if it's not a control character, we want to append it. This might already solve it, but this might also fail. Let's see if this already solves it. Yeah, and you can see this is already solving that. What basically happened is that we kind of like stored the control characters as well, and if we are storing the control characters, they're gonna have an impact on how data is printed. And basically the reset character is a carriage return, which basically moves your head back to the beginning. So basically what we have done, we have like erased something that we have already written or something like that. However, like this is what I want to do now. Basically now I'm fine with that. Now you can see that my properties and values are correctly printed and we are fine with it. Now just to also show this to you when we are already talking about files. I want to quickly show you how you can also write to a file. How I'm going to do this? Well, I'm just going to now spill out a kind of like journal file, that is going to journal what the parser is doing, and it's kind of like providing a log. Let's just call it log file because it really is a log file. So while we are parsing the int, I'm basically just going to open a log file. So I'm going to do a file pointer here again, call it log, and this is going to be equal to null. Then we're going to say fopen as for our log file, or basically pointer to our log file pointer. So pointer, the file is going to be /ini-parser.log. Just to indicate that we are logging in here. And now I basically want to write. I don't want to append. I always want to clear it every time I open it. So write is actually good here so that we truncate it. And of course, as I told you on Windows, we want to write binary to it. So VB, not Warner Brothers, is just write binary. Now what I basically want to do is every time, actually, first of all, let me close the file. At the end of that, I don't think that we used any early return here. No. So at the end, I basically just want to check if it's existing. And if it's existing, I want to do an fclose here, fclose of my log here. And now I'm good. So what I want to do now in here is actually want to log something. When do I want to log? If I report out, I basically want to log. So if the log here exists as well, and I want to basically print to a log, let's basically call this here log buffer to start that. I'm going to make this one a bit bigger, 512. Now I'm basically going to check. No, basically I've recently received a comment that I'm saying too often basically. So I'm going to make sure that I don't say basically all the time basically. So I want to make sure to set the first character to the null terminator as well. And now I'm just going to use strcat, the save string concatenation function, to concat them together and put anything in here. So like that. And I'm basically going to say, actually, I already have that in here, so I could try. No, I'm not really using that. So I basically just want to write, again, basically, I'm going to write property equals to like slash. Then I'm going to, okay, now I have written this into the wrong one. Replace with spaces, of course, not what I tried to do. That one. All right, so I'm going to just add properties. Now I'm going to add the current section. Then I have like the current key and the current value. So let's maybe say section equals that. Then I'm just going to cat that down here as well. So the section is that. The key is that current key. And then we have the value that is going to be equal to the current value. And then I'm just going to string cat a ending slash and a backslash n to basically end that here. To end that file, not basically, completely end that file. What I now want to do is I want to get the length of that string. So I'm going to have a size t write or log length that's equal to string length of my log buffer. I know that is a bit ugly, but I do want to show you writing here. So now we have a length of our string here, and now we can write it. How can we write it? F write to write to that file. It takes a buffer from which it should write, which is our log buffer. The element size is gonna be our log length, and the count is 1 and the stream is log. And this is how we want to write to that file. Now if I execute this, we should now also get next to the config.ini file a log dot I don't know how I called it. We should now get a file. If I refresh that here, I'm getting this ini parser.log file. And if I open this up, we should have an echo out of all of our sections. Okay, so section owner, key name, value John Doe. Section owner, key organization, value ACM widgets Inc. Section database, key server, value, IP address. So as you can see, writing to a file, if you know how that works, very straightforward, just open it and write it out. So really not a big deal here to actually write to that. Actually, I can show you one more thing. You can actually use printf with files as well. You can actually do I think it's fprintf. Yeah, fprintf is the function. Actually, fprintfs is the function where you can actually say I want to write to that file, to that actual log file, and I want to write in the format section. Now I'm writing this again, but it might not be a big deal to show this to you again. So I can actually write to that very more simple. It's more simpler. Without basically now. Or maybe now with. So key, value, you can also do this like that. Which is like, there are many ways to get to Rome. Right. So you can do this like that actually. And then you can add the, let's maybe put this into a new line so that you can see this a bit better, the current section. Current key and current value. I don't know, is that missing string argument? No, it's okay. This is basically replacing all of that code. Yeah, that is way more sensible to do it like that. fprintfs to print to that file. This is way sensibler than that. But you have seen how to write binary data as well. If you don't have strings, binary data is written like that. Very simple. This is simpler like that. You can see it's still looking the same to show you that it's really doing its job and not failing at some point. I'm gonna quickly rerun this and I'm gonna show that to you that it's doing the same thing, right? Actually, as you can see, we already used scanf previously to read in data, you can also use fscanfs to scan from a file. So fscanfs. You can also scan from a stream in the format to basically get some configuration values out of a file to read it in. So this also works, but in our case there was not really a use case for that because we use the state machine for that. But the fprintf is sensible instead of like writing manually. But okay, again, a bit of revisiting how strings work is always good. So that's how you do files, writing files, reading files. Very simple, not hard. Bit of concepts that you need to understand, but a nice feature of the C language. So I hope you enjoyed that. I really enjoyed recording that today. Really was fun doing that stuff with actually something that you can show. In the next video, we're gonna let the user decide which INI file to load. So stay tuned for that. See you in the next video and make sure to like and subscribe. See you in the next video. Bye.